Hi everyone, in this video we are going to be looking at section 27.6, derivative of the exponential function. In the last section we had, before the test, we were given y equals the natural log of x, and that graph looks like the one on the left, and we found that its derivative, or we kind of looked at its derivative being y prime is 1 over x, right? As you get close to 0 over here, the slopes get really steep. 1 divided by a small number is huge. Right about here at 1, the slope is 1 over 1. And then as you move along that graph to the right, the slope kind of gets smaller and smaller. 1 divided by a big number is small. So that's what we previously went through, and we're actually going to use that derivative that we know from previous to show what the derivative of y equals e to the x is. Okay, and the way that we do that is, well, I think it's pretty cool. I'm going to take my y equals e to the x, let's write it over here, y equals e raised to the x power, and we do something that's where we can take the natural log on the left-hand side and the natural log on the right-hand side. Okay, ultimately I'm going to be taking a derivative. Not yet. Let's rearrange things first. Okay, I'm going to use a property of logs that says I can take that exponent there and bring it down in front of my log term. So we have the natural log of y is equal to x times the natural log of e. All right, Now, well, wait a minute. The natural log of e, I know what that is. So the natural log of y on the left is equal to just x, because natural log of e is 1. So we've simplified it a little bit. We just kind of rewrote our exponential equation as a log equation. Now let's take a derivative. Okay, so I'm going to differentiate the left-hand side with respect to x and the right-hand side with respect to x. And in doing that, on the right, we'll write the right side because it's easier. You get 1. Derivative of x is 1, as it always is. On the left, if you remember from the previous section, the derivative of the natural log of something is 1 over that thing. So natural log of y, 1 over y. But because this is an implicitly defined function, we also get to multiply by our dy over dx term. And if we solve for dy over dx, well, I can just take the left-hand side times y, the right-hand side by y. Dy over dx equals 1 times y is y. Well, that's good. That's the derivative, but it's the derivative in terms of y. If I want to represent the derivative in terms of x, well, I go back to the beginning here and say dy over dx is equal to, well, e to the x. And what we see, and it's weird, first time this has happened, that when I have my original function being y equals e to the x, its derivative is the exact same. That's cool, but also a little bit strange. We haven't encountered something like that yet. All right, but that's ultimately the first thing that we need to see here. So our derivatives, the two big ones from this section, the first one that we just talked about a second ago, the derivative of e to the x is e to the x. And, well, what if I have a different base, right? If the base is base e, right, the derivative is the same, e to the x. If I have a different base underneath my x term, so the derivative of b to the x power, well, that is also the same, b to the x, but we also have this extra term times the natural log of that base. Okay, and the reason that that's not in the previous, in the top formula, is because the natural log of e is equal to 1, so that term is not there. So these are the two big formulas, things to learn from this section, and then just apply everything that we've done previously, chain rule, product rule, quotient rule, to these two new formulas. So here are our first two examples, and I want to point out a very important distinction to notice here. In the function on the left, in the equation on the left, we have a base of 4x and an exponent of 2. In the one on the right, we have a base of 2 and an exponent of 4x. They're opposites of each other, if you notice. Now, in taking those two derivatives, one of them, specifically the one on the left, we could have done prior to this section, right? You wouldn't even need to use the chain rule, but I'm going to, right? The exponent comes down inside stays the same, times the derivative of the inside. The exponent is just a 2. So there's no new exponential function here. It's just an exponent of 2, a normal exponent, as we've dealt with previously. And what you end up with for this one, 2 times 4 is 8, times 4 is 32x. Okay? So that is the same thing that we've seen previously. What is new now is the one on the right. When I take my derivative here, dy over dx, the base is 2. The exponent is 4x. So the derivative of 2 to the 4x is, strangely enough, 2 to the 4x. That stays the exact same, but there's more to consider. Okay? The formula from the last slide says we also multiply by the natural log of that base, the natural log of 2, and because we know all this fancy stuff from earlier in the semester, we're also going to multiply by 4. Chain rule. Derivative of the exponent is 4. So the chain rule still applies now to that x term up in the exponent. Okay? And that won't simplify very much. If you multiply the 4 and the 2, that's bad. The 2 is trapped inside the parentheses because it has that exponent. Okay, so really all I could do is maybe I write the 4 first. 4, 2 to the 4x log 2. I would have stopped in the first step. That's good. That's good. Either of those are acceptable answers. Okay, now with this next example, we encounter two e derivatives that also look similar. In the one on the left, my derivative y prime, derivative of e to the 2x is e to the 2x. But we also have to consider the derivative of the exponent, right? That is my chain rule times 2. If you saw it ahead of time, you could just write it as 2e to the 2x and call it a day. That's my y prime. The one on the right, y prime, is derivative of e to the x squared is e to the x squared. But chain rule says times the derivative of the exponent, 2x. Again, we typically write that 2x first. If you see it coming, you can just finish that one in one step. Okay, now we get to one that's a little bit more involved. This one has some functions within functions within functions. So what I'm going to do is throw in some parentheses to emphasize my chain rule steps, right? I have a log of a thing as the outermost function. I have the cosine of a thing inside of that. And then I have e to a power inside of that, and then there's the derivative of the power. So we have a couple of different steps with our chain rule here. Okay, so my dy over dx, or y prime, start with the derivative of the outside is 1 over, because it's a natural log, so we think back to the previous section, the cosine of e to the 2x. And I like the parentheses there. Sometimes the text leaves them off. I think they should be there. It just makes it look clearer that you have these nested functions. Okay, then we go to the next step. So let me change color here. We'll go red. So times the derivative of cosine is negative sine of e to the 2x. Plus the parentheses. There we go. And then the next layer is my e term. Oh, this is the new topic. So the derivative of e to the 2x is e to the 2x. And then that gets multiplied by 2, derivative of that exponent of the 2x. Okay, so there's a lot more that we can throw at you with the chain rule here in this section. To clean this one up, let's see what we got here. I can write my sine over cosine all in one fraction. I can actually bring everything up into one fraction. So negative 2 e to the 2x sine of e to the 2x over the cosine of e to the 2x. And hey, I have a sine of a thing over a cosine of the same thing, so maybe I want to write them as a tangent. Or if you typed that into your calculator, if you typed that into your calculator, maybe it would spit out a tangent, and you'd be like, where'd the tangent come from? Well, that's where it came from. Okay? All right, one more example, and then we can close out this section. Okay, so in this last example, a little bit more involved. We're given a function. I immediately see that it's a fraction, and I grimace and recognize that I'm going to have to use the chain rule, or the quotient rule. And it wants an equation of a tangent line. That's something we haven't done in a while, so we'll review that process. Okay, but the first step to that process is I need my dy over dx. And quotient rule says take the derivative of the numerator first, f prime g minus fg prime. So the derivative of e to the 3x squared is e to the 3x squared, right? It stays the same, okay? But then we multiply that by the derivative of the exponent, I'll put in parentheses, which is 6x. That gets multiplied by the denominator, x squared, plus 1. So there's my f prime g minus f is e to the 3x squared. And then g prime, derivative of the denominator, is 2x. A big ol' over, x squared plus 1 squared. Okay, so there's my derivative. The next step is to answering this question, get the equation of a tangent line, is I need the slope at that point, right? The derivative represents the slope at any point. I need the slope at that one point. So I'm going to take my derivative, dy over dx, evaluated at x equals 1.275. And this is absolutely a calculator question, okay? So take a second, type that in your calculator if you want to, pause the video. And when you do, let's see, you get a big old number. I got about 333.7. So let's say I'm going to round that, so approximately equal to, I'm going to go to the nearest whole, 334. Okay, so what does that represent? That's my m. That's my slope at that point. So I need an equation of a line. I have an x value. I have a slope. I also need a y value. So for that, I take my x and substitute it. Actually, I don't know why I drew that arrow. I take my x and I substitute it back into the original. There we go. Substitute back into the original. Again, you can pause the video and type it into your calculator if you want to. And when you do, you get, what did I get? About 49.97. So you get a y value of approximately 50. Okay, so we need an x, a y, and a slope. And then I go to my point slope formula, y minus y1 equals m times x minus x1. Substitute in what I know, y minus 50 equals 334 times x minus, my point, 1.275. So a teeny tiny x value and a giant slope and a pretty large y value. We'll simplify this guy here. Y minus 50 is equal to 334x minus 425.85. And then when I add my 50 over plus 50, we get y equals 334x minus 325.85. And that's the equation of our line. It's the tangent line to the curve at the point. Okay, so that is it for this section. If you want to sum it up with one basic problem, if I have y equals e to the 3x, the derivative dy over dx is 3e to the 3x. If I have a different base, y equals, I don't want to use a base of 2, 5 to the 3x. The derivative is 5 to the 3x times the natural log of 5, but that one is also has a 3 come down. So 3 times 5 to the 3x times the natural log of 5. Don't multiply the 3 and the 5. You want to, just don't. Okay, that's the end of the section. Please email me and let me know if you have any questions. Thank you.